Hello, everyone. What I want to do now is continue on from last time and pick up where we left off. So in particular, I just want to make a little comment that is an easy consequence of what we did last time, really the definition of a sigma algebra. And this little comment is, if we have a sigma algebra A, and the sigma algebra of subsets of X, then one of the properties is that X take away anything in my sigma algebra is still in the sigma algebra. So in particular, what does this say? This says, well, we know the empty set by definition is in script A. So then X take away the empty set, well, that's just X because you're not taking anything away. That means that X take away the empty set, which is X, is also in script A. So always, if we have a sigma algebra of X, then X is going to be in A. Okay, right. Let me do an example that was actually I did in office hours on Monday, but I think it's a good example to do. It's a very simple example. This is an example you would probably do in like a probability theory course, a more advanced probability theory course. And I don't really want to talk too much about probability theory because I have a video on applications of the techniques and ideas that we develop in this course to probability theory. If you're interested, take a look at that. I actually prove two interesting results: the probability version of Borel-Cantelli lemma and the Kolmogorov 0-1 law. So let's say here we have this example, X is 1, 2, 3. And let's say in this example, F, remember last time F just kind of denoted any collection of subsets of X. So let's say X is the empty set, 1, 2, and 2, 3. So it looks like an interval. Should have a bracket here. Okay, the question is this a sigma algebra script F? The answer is no. And there's quite a few reasons why. Well, we only have to check that any of the properties we know of a sigma algebra to be true are violated. And in particular, we know sigma algebras are closed under finite unions, and certainly take the union of 1, 2, 2, 3. This is not in script F. Let me move this over. I don't know if this is going to appear in the screen or not. Right, so this is 1, 2, 3. And again, this is not in script F. So let's take a look at, and again, there's a lot of reasons why this is not a sigma algebra. This is just one way to show it's not a sigma algebra. So let's describe the sigma algebra generated let's describe the sigma algebra, let's call it script A, generated by script F. So the idea that we're going to do is we're just going to basically keep adding stuff to script F until we know we have a sigma algebra. Hope I can fit it here. I think I will be able to. So I'll put a bracket here. So in particular, we know that there is, like always, there is a sigma algebra containing script f, a sigma algebra of x containing script f. And in particular, that's the power set. So we know the power set has 2 to the 3 elements, which is 8 elements. So we have to add at most 5 elements here. So let's just see what we have to do. Well, like before, we know sigma algebras are closed under unions, so we have to have 1, 2, 3, 1, 2 union 2, 3. Okay, so again, this is 1, 2 union 2, 3. Yeah, and if this is boring, just skip over it. I'm not offended at all if anyone skips over things. We know, let's say, for example, 2 has to be in here because 2 is going to be 1, 2 intersect 2, 3. So let's just keep going. We know that 1 has to be in my sigma algebra generated by script f, because 1 is going to be 1, 2, take away 2, 3. We know 3 has to be in my sigma algebra, and you get the point. 3 is going to be 2, 3, take away 1 second. Yeah, sorry. This is 2, 3, take away 3. Sorry, take away 2. 2, 3, take away 2, which is the singleton containing 3. So let's see, we got 1, 2, 3, 4, 5, 6, 7. So we only have 1 more. Well, I mean, 1 more and we get the power set. We know the power set has 8 elements, there's 8 distinct subsets of the set containing 1, 2, and 3. So last but not least, the one we're missing is 1, 3, which is 1 union 3. Okay. And so, yeah, that's it. So in this case, it turns out that this is, whoops, sorry about that. This is just the entire power set. Okay, so let's talk now about something, well, for the purposes of this course, quite a bit more interesting. And let's talk about Borel sets. I mean, Professor Bachano already talked about this, as I mentioned, but still, just to make sure we're all on the same page, it's not going to take too much time to talk about. So here, X is the real line. Script F, my collection of subsets, I'm defining as, well, a set of all finite open intervals. Not a very exotic example of collection of subsets of the real line, but nevertheless very important. So let's define script B to be the sigma algebra generated by script F. This is often called the Borel. Let's see if I can fit this. It's often called the Borel sigma algebra, and elements in this sigma algebra are called Borel sets. Okay, and we'll see in a moment why this is a very useful idea, very natural idea. So first, homework is following. I'll only collect one of these because the rest, or maybe one or two of them, because the rest are all basically the same. And I want to make clear this is a definition. So this is not a theorem. This is not something to prove. We're defining script B to be the sigma algebra generated by all these open intervals. So homework is that script B is also the sigma algebra generated by all intervals. When I say all intervals, I mean open, closed, half open, half closed, infinite, finite, doesn't matter. This is also the sigma algebra generated by all closed sets. And this is also the sigma algebra generated by all open sets. Okay, right. So, yeah, I think at this point it's good to kind of explain what the point is and why particularly this is a useful collection of subsets of the real line. So the point is as follows. Being a little redundant from the first lecture, we will find a length function, which I call m for measure. And we said we're going to find this script m, which is a collection of subsets of the real line. So in particular, maybe I'll be a little more clear. So this actually will turn out to be, well, yeah, sorry about that. I'll leave that up here for now. So yeah, we're going to find m. Where m satisfies all the conditions that we talked about last time. There's a bunch of conditions that we said, any reasonable length function needs to satisfy. We do want those conditions. So here we're going to find the script m where first of all, m is a sigma algebra of subsets of the real line. And crucially, it'll turn out that B, the Borel sigma algebra, is a subset of script m. So we're going to define script m probably next week, I think. If not the week after, but I'm pretty sure we'll get to it next week. So this is a pretty darn big collection of subsets. All right, so, and I really want to stress what I mentioned last time, that M, the idea is that M is going to contain any practical subset of the real line that you could ever even imagine. Okay. Let me quantify that a little bit, and I'll do some examples to further quantify that. So certainly B contains all intervals. So, right, so certainly intervals are a subset of script M. And remember from last time, the idea is that M is very well behaved on script M. So we have a very nice concept of length. We can measure the length of subsets in script M. So we can certainly measure the length of all intervals. Obviously, that better be true, or it's a pretty crappy concept and definition of length. Two, certainly open and closed sets are Borel sets. So we can measure the length of all open and closed sets. Okay. Well, if, let's say AK is open, if each AK is open for each K between 1 and infinity, K is an integer, positive integer. So yeah, just to make sure we're all on the same page. If each AK is open, well, we know from 2 that open sets are in M. In particular, open sets are Borel sets. They're in the Borel sigma algebra. So that means that the union of the AKs is Borel. And in particular, it's therefore also in M. Okay. So let me call this A. So we have a name for this kind of set. It's a very special set, and the name is a G delta set. Okay. A G delta set, by definition, is the countable union. Sorry, I meant the countable intersection. We know from topology, or what Professor Bachanu talked about somewhere in some way, that the countable union or arbitrary unions of open subsets of the real line is open. So that's not, what I said is true, but it's pretty silly. Because if A is a union of open, countable union of open sets, then A is open. And we know from 2 that open sets are a subset of open sets are in script M. And as I mentioned, we're going to call this measurable sets, or Lebesgue measurable sets. Yeah, sometimes, yeah. I'll probably use both measurable and Lebesgue measurable, but they mean the same thing. Right, so yeah, so we know, or if you don't know, then now you do, that you cannot take infinite intersections of open sets and expect to stay open. The intersection, the infinite intersection, even a countable intersection of open sets, does not necessarily have to be open, but it is still rather special, and special enough to designate, give it a special designated name, and that's G delta sets. The countable intersection of open sets is called a G delta set. Okay. So 4, if each a K is closed. So we know the intersection of closed sets is closed, but the infinite union of closed sets does not need to be necessarily closed. So the union. But we know each closed set is in the Borel sigma algebra. So each closed set is Borel, and because it's a sigma algebra, we know that the union of these closed sets, the countable union, is also in the Borel sigma algebra, and also hence is in script M. So it's measurable. It's a Lebesgue measurable set. So this again is so special that we give it a special name. And I'll say and we call this an F sigma set. So an F sigma set, A is an F sigma set if it is the countable union of closed sets. Okay. G delta A is a G delta set if it's the countable intersection of open sets. Okay, so last but not least, and this might sound really weird, but it's not, as we'll see. Countable unions and countable intersections of F sigma and G delta sets are very natural. We'll do an example of this in a moment. So countable unions and intersections. And differences, set differences of sets of the form 1 through 4 are Borel, and hence they're measurable. Right? So yeah, you really, this should really drive home the idea that any practical set you could possibly ever imagine is going to be measurable, right? We will prove that there exists a non-measurable subset, so it does not contain everything. But we'll get to that later. And we will prove, I believe we'll prove, don't quote me on this, but I believe we'll prove that actually there are more measurable sets than Borel sets, but that might not mean much because we haven't even defined what a measurable set is. We'll do that next week. All right, so let me just do 2 easy examples that indicate how the concept of an F sigma set and a G delta set is very natural. So I can write this half open, half closed interval very naturally as a one second about that, as a G sigma set. And from elementary analysis, sure you've seen examples like this. So this is definitely G delta. So in particular, well, yeah, this is G delta. So this is a G delta set. This is the countable intersection of all of these open intervals. And yeah, if there's any doubt, you should check this yourself. And also the same set is F sigma. You can very easily write this as the following countable union of closed sets. Here I'm assuming A is less than B. And in this union here, if A is not less than or equal to B minus 1 over n, then by definition, this is just going to be the empty set. So, yeah, so, and you can do the same thing for open A, closed B. So any half open, half closed interval is going to be both the G sigma and an F, G delta and an F sigma set. I might get my Greek letters mixed up. I really hope I don't, but yeah, any half open, half closed set can be written as both a G delta and F sigma set. All right, so let me do a much more interesting example, and one that we really all like to, well, at least I like to put on the prelim every now and then. And whether I like it or not, whether I volunteer or not, I'm usually often the one who writes prelims. So good to pay attention if you're planning on taking the prelim. Right, so a fact that you probably all know, but I'll just remind you, is that if I have a continuous function from R to R, so if this is continuous, then the inverse image of any closed interval, and I hope I'm not patronizing by writing this out, but just make sure, again, we're all on the same page here. This is just a set of all x in a real line where h of x is between a and b. This is closed. All right, so let me prove the following. Let me do the following example. And this will be a very natural example of where countable intersections of F sigma sets arise. So let's say we have a sequence of continuous functions from R to R. And let's say we have a function R to R. So for each n, Fn is continuous and F itself is continuous. So I claim that the set A, which is not a very exotic set, it's a very natural set, the set of all x where Fn of x, the sequence of real numbers, converges to F of x. This is the countable intersection of F sigma sets. Okay. And this is a very natural set. You might want to know what x, Fn of x converges to F of x. If you're just given an arbitrary continuous function f and an arbitrary sequence of functions Fn. So this might be empty. There might not be any. This might be the whole real line. There might be a lot of x where Fn of x converges to F of x. Whatever it is, you might want to know its size. You might want to know its length. Okay. So the punchline here, well, I mean, one of the punchlines is that this is a typical prelim problem. This probably actually is a former prelim problem. I'm pretty sure. I myself have probably put it on one of the prelims. But the point is that A is a Borel set because we know F sigma sets are Borel. And because this is a sigma algebra, Borel, this is the Borel sets or elements of the Borel sigma algebra. We know countable intersections of F sigma sets of Borel, and thus A is Borel, and so A will be measurable. And this exclamation mark is just to emphasize that A is measurable. Okay, so how do we prove this? The proof is actually not too bad. I'll go very slowly because it might look a little funky if you've never seen this kind of logic before. So let's write out what it means. And when I write X such that, I mean X in the real line. I don't really feel like writing X and R all the time. So we have to quantify what it means for Fn of X to converge to F of X. And we all should know how to do that in terms of epsilon delta. So this is just a set of all X, where for any epsilon bigger than 0, there exists n, natural number n, where for any n Fn of X minus F of X is less than epsilon. Well, the only thing is, for any epsilon bigger than 0, we're considering an uncountable many number of epsilons. And when you do problems like this, uncountable is often not good. And you try to avoid that. You try to kind of rewrite this in a better way, just involving countable things. What do I mean by that? Well, there exists n in the natural numbers. That's good. The natural numbers are countable. But we can do an obvious thing, and if it's not obvious, you should definitely prove this yourself. So instead of any epsilon positive, let's write it like this. For any natural number big M, there exists an n where for any n, little n bigger than big N, Fn of X minus F of X. So to represent an arbitrarily small number, we can just basically take 1 over M for any natural number M. The larger M gets, the smaller 1 over M is. And I'm allowed to do less than or equal to because, both epsilon and M are arbitrary. And I need less than or equal to, I'll tell you why in a moment. Okay, so let's start to unravel this a bit. So we got to move things over a little bit. And I don't know if this is appearing. I apologize if it isn't. This is less than epsilon. Okay, so I can write this for any M. That means this has to be true for all M. And we can write that using basic set theory by an intersection. And again, if I shouldn't say again because I didn't mention this before, but if this looks a little strange, then I highly suggest you prove this in the sense that prove, well, let me just write this down and I'll tell you what to prove in a second. So if you have any doubts, then I would highly suggest you prove what I am circling. And you do that, this really, I could, really, yes, technically have had this as a homework in Introduction to Proofs, AMAT 299. all you really do is just prove the left-hand side, or you prove that this set here is a subset of this one here, and vice versa. Okay, just prove one is a subset of the other. Okay? It's really not very hard. So I want to do the same thing for there exists, and you should be able to understand and recognize that that's basically doing unions. There exists means that, for at least one n, we have to have something true. So I can write this as the following. So the intersection m, I want to make sure I wrote m. Yes, I did. The intersection m from 1 to infinity union n equals 1 to infinity x such that for any n bigger than n, this is less than or equal to 1 over m. And again, here, I'll do it in blue. Here, the idea is that what I'm circling, the two things I'm circling in blue are going to be equal. And if you have any doubts, then just prove that one is a subset of the other and vice versa. So the two things that I'm circling here are going to be equal for each fixed m. And again, really, that should not be too bad. Both of them are saying basically x is in this set for at least one single n. Okay, and last but not least, so it's really a pain to keep writing like brackets, so we usually don't. The brackets are implied, and certainly I very much encourage, so this probably is new, so if this is a little wishy-washy, or even you want me to prove what I'm saying should be, you should try yourself, come to office hours and I'll be happy to. Well, I mean, I expect you to at least try to prove it first, but if you try it and you're not really sure how to do it, I'll be happy to help you out. I'm always happy to answer questions as long as people make a good faith effort. So last but not least, and I will write one single bracket. So yeah, I want to finally write this in terms of a intersection. Well, so x is in this yellow set if for all n bigger than big N, and well, that means natural numbers, of course. So we can quantify that by x is in the yellow set if it's in all of these sets. So here's the beauty of doing this. What have we accomplished? We've accomplished a lot. This, I'm running out of colors here. I guess I'll use purple. You should know what kind of set this is. This is a closed set. Why? Each Fn is continuous. F is continuous. Fn minus f is a continuous function on the real line. This is simply the inverse image of the closed interval 0 to 1 over m with respect to the continuous function, the absolute value of Fn minus f. Fn minus f is continuous. The absolute value of Fn minus f is also continuous. And we know that the inverse image of a closed set is closed if the function is continuous. Well, that's wonderful. What does that tell us? That tells us that, well, because what's in the purple is closed, what's in the, I don't even know what color this is, pink, I guess. This is also closed. And we know that the intersection of closed sets is closed. So in particular, the countable intersection of closed sets is closed. All right. I'll use green here. So we're almost done. Well, we know that this green here, I guess I'll put another bracket just to make sure what we're doing is absolutely clear. I forgot the other bracket. Sorry about that. Kind of why brackets are a pain, because you sometimes forget them. And again, I apologize if I'm going at a snail's pace here, but okay, green, this was it. So, right, by definition, the countable union of closed sets is F sigma set, definition. So finally, this whole thing is the countable intersection of F sigma sets. Okay. So yeah, so this rather innocent looking set here is the countable intersection of F sigma sets. And again, the whole point is this is a set that will therefore in the next 3 weeks or so be able to find the length of, because there is a well-defined length that can be applied to this set. Because of the sigma algebra properties, it will be in this script M, where my length function is very well defined. All right, so enough of that. Let me very briefly start talking about outer measure, which is, you kind of should think is kind of the initial candidate for M, and really in some, basically it is what little m is. The issue is just we're going to have to restrict, we're going to have to restrict the sets we're measuring. So yeah, so my outer measure is literally M, but anyway. Okay, so yeah, we've finished all that's relevant in chapter 1 for our purposes. So let's start chapter 2 in Royden and Fitzpatrick. I'm going to do everything very similar to the way they do it, because that's the way I'm familiar with it. Done it this way twice before. Okay, right, so I guess I'll be maybe a little redundant. State the chapter goal. Chapter goals basically do what we talked about in this video and the previous video. That is find this length function and the sigma algebra of measurable functions, functions that we can measure the length, measurable functions, sorry, measurable sets, sets that we can, this little m is well defined on. Yeah, and the sigma algebra M, where M satisfies the conditions from the last video. Okay, so let's get to it. Okay, so let's say A is a subset of R. So let's define the outer measure M star. So as I said, this is going to be the definition of M. This will be the definition of M here. But just to emphasize that this function here is defined for all subsets of the real line, we give it a new name, M star. So really this M here is going to be, we'll take a little time to define script M, but really M is going to be what I'm describing, this M star here, restricted to these nice sets. So M star, what is this? It's actually not a very subtle definition. I'll just write the definition down and then explain in words what it is. Actually, I'll write it down because I think it's worthwhile for you guys to write it down. So this is the formal definition. It's the infimum of all these numbers here. Okay. Yeah, and if it turns out that every single one of these sums is infinite, if that's just unavoidable, if all of these red sums are infinite, then we define M star of A to be infinity. Okay. Right. So, right. So what is this really? Well, morally speaking, infimums are kind of like minimums. Minimums don't always exist, so infimums are like the next best thing. So informally, I like to think of this as the minimum sum, which might be infinity. That's okay. The minimum sum of lengths of open intervals needed to cover A. And in general, we really don't define uncountable sums. So when I say sums, I mean like, we're dealing with countable covers of A. Okay, so that's the intuition. So, in my opinion, when I write this down, this is not a unreasonable definition of length. It's reasonable. So let's start to prove some properties of this M star. And yeah, this is called outer measure or Lebesgue outer measure. Yeah, I'm only going to prove a few simple properties. So let's prove the following proposition. If A is a subset of B, both are subset of the real line. Obviously, outer measure is only defined for subsets of the real line. Then M star of A is less than or equal to M star of B. It's kind of sort of better be true, otherwise this doesn't make sense. And what's the proof? Well, let's assume m star of b is finite. If m star of b is infinite, then I don't care what m star of a is, finite or infinite. Anything, anything non-negative, including infinity, is less than or equal to infinity. So, yeah, so I can, this is trivial if m star of b is infinite. So let's assume it is finite. So I'm actually dealing with, so so I'm dealing with, at least for m star of b, a set, an actual subset of, or I'm dealing with a set where there's at least one single actual positive real number in it. So then the infimum certainly makes sense as a real number. The wrong direction. Okay. Right. So by definition of an infimum, let's say epsilon is bigger than 0. So m star of b plus epsilon is not a lower bound of this set here. It's not a lower bound of the set that I'm circling, because the infimum is the greatest lower bound. M star of b, well, I guess really b. So let me just replace this with b. Right, so because it's not a lower bound, by definition, we can pick a countable cover by open intervals where m star b plus epsilon, and again, the reason is m star b plus epsilon is not a lower bound of this red set. So you can pick one of these where this is bigger than this sum. All right. Right. However, so not a very subtle proof, but still kind of gives you a little glimpse of the mechanics used when proving facts about outer measure. Well, A is a subset of B, and B is covered by these open intervals. Well, m star of A, go back to here. Well, m star of A is a lower bound of all these sums. So m star of A is less than or equal to this one particular sum. But this particular sum is less than m star of b plus epsilon. So we play this silly game of m star of A is less than or equal to m star of B plus epsilon for all, I guess it's really less than, not that it matters. So that implies m star of A is less than or equal to m star of B. And that finishes the proof. And I'm kind of inconsistent with my little finishing the proof things. Sorry about that. It's clear when I finish proofs. All right, so one more thing. So I want to prove the following proposition. If C is countable, so it's a countable subset of the real line, then C has 0 outer measure. So we really just say, actually, if this is true, because it'll turn out that any such set is measurable. We just say C has measure 0. If this is true. Okay, and the proof is not too bad. Let's say epsilon is positive. So we have to come up with a nice countable cover of yeah, we got to come up with a nice countable cover for C. The infimum is, and we want the sum of the length to be less than epsilon. The infimum is what the outer measure is. So if we can get that true, then the infimum is less than or equal to epsilon for any epsilon. Hence we're done, because the infimum then will be 0. So what do we do? Well, we don't, yeah, so we got to be a little tiny bit careful. Let's say, but not too careful. Let's say a k, the left endpoint of my interval, is ck minus epsilon over 2k plus 1. And let's say bk is ck plus epsilon over 2k plus 1. Well, there's really not much to prove here, in the sense that this is obviously a cover of C. Each little ck is in AK and BK. So C is a union of all these. I mean, C is this countable set. So certainly this is true. So by definition, again, this is the infimum of the sum of all these lengths of open covers of C, countable open covers by intervals. So in particular, the infimum is less than or equal to this one particular length for this particular countable cover of C by these intervals, open intervals. So this is going to be equal to bk minus ak. You can check easily. Well, it's just epsilon over 2 to the k. So this is going to be and the reason why we want 2 to the k, actually it doesn't matter if we do really 2 to the k plus 1 or anything we want. We really just want, this to sum up to epsilon times 1. So however you really want to do it, doesn't matter. Probably the simplest way is, just doing epsilon. You're doing it like this here. Particularly, we know this is infinite geometric series. Plug into the formula. This is epsilon. Right, so this is true for any epsilon whatsoever. M star, the outer measure of C is less than or equal to epsilon for any epsilon whatsoever. So that implies that the outer measure is 0. So you might be curious about the converse. Converse is false. So there exists C uncountable where m star of c, so c has 0 measure. The most simplest example is what's called the Cantor set. We'll talk about that later. Professor Bracciano, I think, even talked about it. Yeah, so I'm going to end here. So next time I'm going to prove the following, which actually is one of the more challenging things in this course to prove. And it looks so innocent. But so next time I'm going to prove that the outer measure of a open interval a to b, I really probably should put 2 brackets, but that's just a pain. So is just its length. Actually, well, I'm actually really going to prove that the outer measure of the closed interval a to b for 2 real numbers a less than b is going to be b minus a. And I want to do that because I'll be able to use compactness. I'll be able to use the Heine-Borel theorem. Okay, this is a bit long. Sorry about that, but good place to stop. And office hours on Wednesday as usual. So, all right, so long. Take care. Yeah, and do give me the midterms by Monday. I believe I said Monday. And I'll have a new homework based on all the things we've done so far by the weekend, by Monday at the latest. And I'll have it assigned rather. All right, so long. Take care. Till next time.